So in this tutorial, we're going to introduce the concept of work to energy. We should have started this in class and perhaps finished it. If we didn't, then you can fast forward to the part where we didn't get to in class. I'm going to try to make this quick like we were doing in class so we can get to the conservation of energy video. Okay, so we're going to talk about what happens when you do work. All right, when you do work, there are three cases. You can have no opposing forces, you can have opposing forces that are conservative, and you can have forces that are non-conservative. So we're going to look at each of the three situations and figure out how to calculate the amount of energy you have and the type of energy. So the first situation, no opposing forces, is we said in class was work goes to kinetic energy. Okay, KE. And that's the energy of motion. And so we want to come up with an equation that tells us how much kinetic energy you get when you do work. And that work is a force times a distance, and that really translates to MA, and our distance would be a change in position. And we talked about in class that A times delta X from kinematics is really just equal to 1/2 your final velocity squared minus your initial velocity squared. So if we put it all together, we can see that change in kinetic energy when you do work is equal to 1/2 mass times v squared minus v naught squared. All right, so we can put that over here, 1/2 m v squared minus v naught squared. So kinetic energy, if we want it just for one instant, this becomes 1/2 m v squared. So it goes by the mass and the velocity. And an important thing to remember is that kinetic energy goes by the square of the velocity, so it grows quickly, whereas momentum only goes by the velocity to the first power. So there will be practice problems after this for you to work on, but make sure you look this over and you have it in front of you. All right, what if we do work against a conservative force? A conservative force tries to bring the object back to its original position. Okay, examples of this are gravity, we mentioned in class, trying to lift something above the ground. Gravity wants to bring it back down. And something we'll talk about later on in the next few days are springs. Springs, when you stretch certain things, try to bring them back. So there's an energy associated with them. That work goes towards potential energy. And we're going to give this symbol potential a capital U. All right, there are many types of potential energy, so we're going to put subscripts with them. In fact, if our conservative force is gravity, we lift something above the ground, then we give it, not kinetic energy, we give it gravitational potential energy, U sub G. And we want to come up with a way of calculating the amount of potential energy you get when you lift something above the ground. And it doesn't matter how we lift it. We could use a ramp, we could use an elevator, we could use stairs, we could go straight up. The beauty is the amount of energy it has is the same. And it's equal to the work to lift it straight up, which is equal to the weight of the object times the distance we lift it, which is the height. If we lift something straight up, we get mgh. If we try to use a ramp, then the force we'd have to exert is W parallel, which would be mg sine theta, that's the parallel force, times the distance, and that we learned before is nothing more than mgh. And if we try to use this curved path, it turns out that the change in gravitational potential energy is the same as straight up. Okay, so in other words, it doesn't matter what path we take, the work done to raise an object to a different height is independent of the path taken. And I cannot stress how important that is. That's why we have the 5 stars there. Okay, we'll exploit that. But again, when you lift something above the ground, it doesn't matter what path you take, when you did it, how you did it, all that matters is the change in height. So if we want to calculate the amount of gravitational potential energy, you take the weight and you multiply it by the height. And the height, what you call 0 is arbitrary. We'll talk more about that in class, but it can be whatever height you want it to be as long as you're consistent within that situation for all other events. And any change in gravitational potential energy will be mg delta h. Okay, so again, there will be practice problems with that on the preceding pages. All right, if the conservative force is elastic, then we'll eventually talk about elastic potential energy, but that will come later. Okay, so the last situation we have to do is when you do work against a non-conservative force. Non-conservative force doesn't bring the bag to its original position. The classic example is friction. Okay, so in this case, work goes to thermal energy. And thermal energy, I'm going to call Q. I might change my mind later, but we'll call it Q now. So we have an equation for potential, or kinetic. Kinetic is equivalent to 1/2 mv squared. we have an equation for gravitational potential, which is mgh. We want an equation for Q. All right, and it's actually very simple. Q is gained by the work done on it, and the work done on it is the force of friction multiplied by whatever distance over which it acts. So Q is nothing more than a work equation. So when you do work, to summarize, you can get this if there's no opposing forces. If there is a conservative force opposing you, namely gravity, you can get this. And if there's friction, you can get this. Or you can get all three at the same time. Or you can get two. So for example, if I slide a desk across the floor with a force greater than the force of friction, then the desk will accelerate, which means it'll gain speed, which means it'll gain kinetic energy. But not all my work goes into kinetic energy because of the opposition of friction. So not only will we generate more kinetic energy, we'll get some thermal energy in the process. So we would say W in that case goes to KE, the change in kinetic energy, plus some thermal. Another example is if we lift something straight up in the air with a force greater than its weight. In that case, our work is going to an increase in potential energy plus an increase in kinetic energy. All right, I'm out of time. The announcements came on. So do these practice problems that follow. The answers are given. Very, very important you get the basics down before we go on to the more complex conservation of energy.